Alrighty, guys. So today's lab is going to be lab 9, which is carbon in the forest. So what we're essentially doing is figuring out how much carbon is released during a wildfire. Particularly, we're looking at the Clover Mist fire. We're basically just looking at Landsat images that covered this area in 1987, 89, 98, and 2008. So we're first determining how much carbon and like carbon trees and forests in general are actually able to store. And then we're able to actually calculate how much carbon has been burned during this Clover Mist fire, so we can figure out kind of what the impacts are of this wildfire for carbon dioxide levels and whatnot, right? So first off, you're going to be watching the video that I posted on the assignment submission page. So it's basically goes into why naturally occurring wildfires are necessary and why we really do need them to be able to continue properly managing different forests because of the impacts with fire suppression. For example, longleaf pine has forever and ever been suppressed since European colonization, essentially, partially due to the turpentine industry as well. But longleaf pine used to be all across the southeastern United States, and it's a fire-based ecosystem. So it relies on frequent fires that are low severity. So when we get this fire suppression, and say we have a large thunderstorm come through, and lightning strikes a tree and causes a massive wildfire, there's a much higher fuel load in that area that's been suppressed for a while. So it burns at a much higher rate, and those are the really dangerous wildfires. And we see the same thing out west all the time. But regardless, so but that's part of the reason why naturally occurring wildfires and prescribed burns that we do, especially out here in the West, are so important to just maintain lower fuel loads and try to mitigate any sort of massive carbon release like what we saw in the rainforest, in like Amazon rainforest last year. So for the questions part, you're just kind of calculating how many number of townships were 100% burned, 75% burned, 50% burned, or 25% burned. So you're looking at figures 1 and 2 in the reading for this. And so then you're going to calculate your total townships burned. So that equation is in the text on page 126, but I'll just go ahead and write it down as well. So total townships burned is going to be P equals, whoops, not P equals, sorry, P plus 0.75 times Q, right? So we're taking, we're calculating and managing for the fact that it's only 75% burned. So we're just numbering how many, we're counting how many number of townships are 75% burned. And then we're going to add 50% burned times our, which is represented by T. And then the same thing for 25% burned, right? So, and all of that is going to equal our number of townships burned. All right, so then we have to calculate our area burned. So in the text, we're given that one township is equal to 36 square miles, right? Or you can also represent it as L squared, right? So then we're going to multiply that by the total townships that we calculated. So that's represented by B, right? So we're just going to multiply that by B. All right. So that gives us our total area burned in miles squared. And then we have to convert it from miles squared to hectares, right? So that's the metric system versus our weird system that we use here. And it's even given to you what the conversion is there, right? So 1 mile squared equals 259 hectares. So the next part, calculating what the volume of each tree is, because we're slowly building up to figure out how much carbon is stored in each tree, and therefore like how many or how much carbon has been stored in the actual forest itself. So we're given our equation to find the volume of our tree in meters cubed, right? But remember, in our text, we're given diameter, not radius. So we have to divide our diameter by 2 to be able to get our radius amount, right? So this is for number 3. So our equation is just pi r squared times the height of our tree. And we have to look at all of our units as well, right? So pi is just going to be, of course, 3.14. And we're going to multiply that by our diameter divided by 2. And we've got to square that value, right? That's very important. A lot of people forget to square this value and then they end up with the wrong answer. All right, and then we're going to multiply that by 16 because we're given in our text that our lodgepole pines are 16 meters tall, right? Then that'll give us our answer for number 3. From there, we have to calculate what our oven dry biomass of wood is in kilograms, right? Because we'll have to find the weight of the tree. So for this, a lot of people mess this one up as well, right? So all you have to do is use your equation that's given. So it's B equals V times S times W. So V is just the volume of tree in meters cubed. We calculated that already. And then we multiply that by our dry specific gravity of wood. And we get that from our table on page 128. And we multiply that by 1,000, right? Because we know that W is the weight of 1 meter cubed of water, and we're given that's 1,000 kilograms. So we take our answer from number 3A, right? So we take A, what's the wonky A times whatever our specific gravity of wood is. So we're using lodgepole pine right now. So you know that is 0.41 for our specific gravity. And we're going to multiply that by 1,000. Right? So for all the other tree species, you still use the same volume of the tree from 3A. I know it's not intuitive to do it that way simply because all of these different trees are going to have different tree volumes, which is absolutely correct. But for whatever reason, that's just how I have you guys do it. So you know kind of what the principle is behind it, right? So this is just for the lodgepole, right? This is the value that changes based on the species. Tree species, look at the table on page 128. Right, okay. So from there, At 3C, you're just figuring out what the total weight of the tree is, including the root system. And we're told that the root system scales out to about 20% of the above ground weight of the tree. So we have to multiply that by 120%, right? So 120% just needs to get converted to a decimal, and then from there you're able to calculate how many kigs there are per tree. And then for 3D, let me go ahead and clear this out. Cool. So for 3D, we have to take the total weight of kilograms of all eligible pines that burned in the fire, or we have to calculate that rather. So we are told there's 100 trees per hectare, right? Because we're assuming that there's 10 trees per 0.01 hectares. So we do 100 trees per hectare. We're going to multiply that by our 3C answer. I'm going to multiply that by the number of hectares that you calculated. And that was on page 126. And then we are told that the average carbon content is generally 50% of a tree's total volume. So all we have to do with that is divide our weight by 2, right? So that one's really straightforward. And then for 3F, we're given how they calculate the ratio of carbon dioxide to 1 carbon, right? So there's 3.6663. So for 3F, all you have to do is take your answer from 3E, right? So that's our carbon amount. We're going to multiply that by our ratio to carbon dioxide, right? Which is 3.6663. And that'll give us our answer for that one. On the following page, all you have to do is just critically think about what the question's asking for, answer incomplete sentences. Pretty much all of the other questions are really straightforward. But as always, if you have any other questions that I didn't go over, or if you're confused about a concept, feel free to pop into the Zoom session and email me, whatever works. And these are weird times for all of us, so just bear with me with it. And then the last bit of information to just quickly go over is on page 133. You have to look at your Keeling curve, which is at the beginning of the literature. Well, sorry, at the end of the literature, which is figure 5. So just think about, for like question 15 especially, a lot of people get confused about this question. So just think about the seasonality effects of trees, particularly deciduous trees, right? What trees gain and lose every season, how that might affect their carbon sequestration or sequestration. And just critically think about that when you're answering those questions, all right? But hopefully you guys aren't confused at this point, and yeah, have a great week.